Hello, welcome. Welcome to second year for many of you. Math 2921 is where you are, so if that was not what you were expecting, you can make a quiet exit if you want. I'm Chris Listry. I will be the lecturer and coordinator for this subject. I've moved on to this subject this year, so this will be my first time teaching it through with you. Hopefully it will be fairly smooth, but the first time you teach a class, sometimes the timings are a little off, so you know, we'll deal with that when it comes up. So what are you in for? The way this subject works is that there are 3 hours of lectures, all of which begin at 9 o'clock, and I enjoy that about as much as you. I'm really grateful for those of you who turn up. It is much easier lecturing to a room full of people, even when none of us want to be here at this time of the morning. So, Wednesday 9 to 10, Thursday 9 to 11. There is also a seminar on Thursday from 12 to 1, and what that seminar will mostly be is computer worksheets. So the computer worksheets will often have sort of visual, tactile examples that you can play with and get a feel for yourself. Because the thing about vector calculus and differential equations is they are quite concrete ideas with very geometric interpretations. And getting used to these things is really, really important. However, that won't be the only thing that happens in the seminar slot. The thing that you have to be absolutely aware of, and this will come back on the next page, is that the seminar slot will be when the mid-semester exams are held. So even if you don't normally come to the seminar because it's recorded, in week 7 and week 11 you absolutely have to. Now, there are 171 students enrolled in this class, and if you look around you will notice there are 160 seats. We are working to rectify that, and in the exam weeks we will actually have a second room booked, and you will have to allocate to one or the other. You don't need to worry about that now, but keep an eye on the announcements so that you know more about that as it arises. I will use the announcements to communicate with you throughout the semester. The announcements will go up both on Canvas and the Ed Forum to give the most chance that some of you manage to see it, if only by accident. It's really important that you stay aware of these. I will assume that everyone is reading the announcements. If there's something in the announcements, I will take it as you all know it. That is a delightful fiction, but if you don't know it and I announced it, it's your fault and not mine. So that's kind of the logistics of how this is going to work. The subject is called vector calculus and differential equations, and what these two areas really have in common is that this is where linear algebra and calculus kind of become one thing and not two. Everything we do throughout this semester will be motivated through a framework of linear algebra, even though in first year they were kept sort of separate. What you really learn when you start to reach this level of mathematics is that linear algebra sits underneath almost everything, and we're going to make that really explicit throughout this entire course. So the first half is vector calculus, and there is a free textbook available to you, Calculus 3. I will tie in the lectures to sections of that textbook so that you can follow along. The textbooks are linked to on the Canvas page. If I've done this right, you should see the Canvas page. Okay, so the Canvas page. Everything here will be linked to at the end of semester. So these are going to fill up bit by bit. I'm going to start with the blank lecture notes, and at the end of the week I will put up the complete lecture notes each week. The tutorials and the solutions, the computer worksheets, which will come, which you'll see more about on Thursday, the assignment and quiz solutions, and links to the recommended reading, which is the 2 free textbooks and another useful piece of reading that will be helpful. So here is the link to Calculus 3, which is full text available from the library. And in the second half of the course, we'll be building around this textbook here, Elementary Differential Equations with Boundary Value Problems, which is fully available as online notes or a downloadable PDF. So I wanted to make sure that you don't have to go shelling out lots of money for a textbook, but the textbook is really helpful. This class is theory heavy, and you still want to supplement that with examples. This is where you find lots of worked examples, so please make use of these. This final reference here, Vector Calculus and Introduction, is by Daniel Danners, another member of the school. He actually used these as the notes in, I think, 2018 and 19. They are still really good notes. There are some divergences from how we teach it now, but broadly speaking, the themes are the same. You should still come to my lectures and you should still read my notes, but these are a really great supplement to the taught material this semester. Okay. Back to this. So that is the layout of the course, but now the bit that you all... Oh, one other thing. Right. This semester has a lot of content, like a lot of content. And there are some weeks where 3 hours might not quite work unless I absolutely rip through the material. I would much prefer to explain it well and take up a little bit of the seminar time to explain the material properly than do a bad job. So I don't plan to do this much, but there are a few weeks where I might lecture into part of the seminar. It's recorded, it will all be available online. I know no one wants 3.5 hours of lectures in a week, but again, I'd rather do a good job. Week 5, watch out for that week. That was when I made the decision. So week 5 is when the rubber will really hit the road. We'll talk about that when we get to the actual teaching, but like circle week 5 on your calendar. Okay. That's good knowledge. All right. The bit you've all been waiting for. How am I assessing you? I am assessing you via a whole array of things. You have tutorials. Tutorial participation is not a high bar. If you were there and you were converting oxygen to carbon dioxide, it counts. So you need to attend at least 10 weeks. Each week is worth 0.5% for a total of 5%. Advanced math. 10 times 0.5%. There are 6 tutorials. Each of the tutorials is taken by one of 3 tutors, all of whom are excellent, experienced tutors. I'm not taking any of the tutorials myself, but I will be trying to get to a different tutorial every week, which means you should expect me to appear in your tutorial about twice over the course of the semester. I want to do this so I have a chance to get to talk to all of you, kind of get to know you a bit, and to make you feel comfortable talking to me. It's really important that that happens so that, you can ask me questions and know that I won't judge you particularly harshly. There are online quizzes. I cannot tell you how kind these are. These are there to make sure that you are continuing to engage with the subject and have a pulse. Don't lose sleep over these. You have 60 minutes to do 5 multiple choice questions. For context, last year you had 30 minutes to do 6 multiple choice questions. The thing is, with testing that I'm not in the room for, you can use AI. You're allowed. The university lets you. But I'd rather you try and not do that. However, I know you're all neurotic type A overachievers who want that perfect wham. That's why I'm giving you 3 chances. Have a go on your own for the first chance. Maybe think about what you didn't know, go and revise it, come back in and do the second chance. The questions are the same and you have more than enough time. If you crash out on the second one, I don't know, in the third one, put all the questions into ChatGPT so you can get your 1%. I don't care. If you failed to learn something at that point, that's on you, not me. All right. The due dates in the unit outline are a little bit off because there was a transcription error between the 2025 and 2026 dates. Could be someone's fault. I refuse to acknowledge that it's mine. So if you're confused about the dates, what you want to do is you want to go over here to this quiz tab, and it will tell you when they are due. These are true. Do them. You've got so many chances. Like, you should all get 5 out of 5 for this. You really, really should. There is also the assignments tab, which has the assignment. We'll talk about that in a bit. Okay. The assignment. Hey, it's a bit. The assignment is due in week 5. It is worth 10%. Again, it's assessment that I'm not in the room for. I don't mind you supplementing that by asking friends or any other resource you might want to use. Peer learning is a really important learning strategy. Talking about it with other people, it will be a bit tricksy. It's an assignment. Working through it together is absolutely fine. I'd prefer you write it up yourself, but I really, really don't mind you doing that. I think it's helpful. Of course, all of that adds up to online quizzes are 5 times 1%, which is 5%. So 5 plus 5 plus 10. All of this is 20% of your grade, which means these two things here are 80% of your grade. These are the bits where I get to see what you really know. There are 2 10% mid-semester tests. They will be 40 minutes long, and they will be held in the seminar class of week 7 and week 11. And as I mentioned before, you will be spread out over 2 different lecture rooms, so please keep an eye on the announcements so that when you can allocate to one or the other, you are able to do that. And of course, in exam period, there is a final exam worth 60%. You've got to expect that the final exam is the biggest thing. It's the comprehensive final exam that tells me everything you learned across the whole semester. In first year advanced, you might remember that the exams between the mainstream and the advanced stream were quite closely aligned. Same multiple choice, 2 out of 4 short extended answer questions the same. There may be some similarities between the exams this year, but nowhere near that level. This is where the material does diverge a little bit, and we need to sort of poke you a little bit harder. So, you are still able to move freely between the classes, but you should expect that the final exam will be a little more geared towards the specifics of what you're being taught in this class, which is probably a benefit. Okay. Course structure. Assessment, frequently asked questions. Questions I've already received by email and thus I determined to be frequent. Will lectures and seminars be recorded? Absolutely, and live streamed. Please turn up anyway, empty rooms are awful. Obviously, you can't, if you've been relying on the recordings for the seminar, that won't help you in the mid-semester test. That will not be recorded. I have consultation hours. They will be Thursday from 2:30 to 3:30 p.m. That overlaps an hour barrier, which means if you have stuff until 3 or stuff from 3, you should still be able to find a time to come and see me. I am in Cars Law 237. Probably should have put that there. Let's move everything so it looks like I planned that. Cars Law 237. If this time doesn't work for you, you can email me. I'm pretty happy to speak to students as and when they need. If you have a quick question, you are welcome to come by my office and see if I'm free. If I'm not free, I will at least be polite and I will sort of help you find another time. So not a total open door policy, but you are absolutely welcome to come by, particularly if it's just a quick question and you don't want to wait 4 days or something. Can I go to a different tutorial? 171 students enrolled in this class means that it is pretty full. We aim for 27 students in a tutorial, and 171 divided by 27 is very nearly 6. But not every student attends every week, and students will shuffle around, and you are welcome to try a different tutorial, with the caveat that if the tutor thinks the room is too full, then they can decline. So go try a different tutorial. And if that works, brilliant. And if it doesn't work, you're allocated to something. You should go there. So yes, if the tutor agrees that there is room. There's always room. Can you ask questions on the Ed Forum? You can. I won't be answering the Ed Forum every minute of every day, but I will set aside at least 2 blocks in the week where I will go through and deal with the unanswered Ed Forum questions. And of course, you can help each other by doing my job and answering each other for me, which is why it's a public forum. You're allowed to do that. So please feel free to use it. I'm happy to help. And of course, many of your peers will be happy to answer your questions as well. And I strongly encourage that. Okay, that is kind of the administrative part of the subject. Before we keep going, I don't have perfect peripheral vision on my right-hand side. So if your arm is up on this side of the room and I am completely blanking you, just wave it around a bit or let me know. It's not personal, it's just medical. Okay, so there is that. All right, are there any questions about stuff? Yes. Yes. All of the tutors can mark attendance for any student. But. These 10, don't get clever, have to happen in different weeks. Don't think you can knock off 6 tutorials in week 1. Any other questions? It's okay, I don't expect many. Yeah. It is a very friendly computing seminar. It is not a deep amount of coding. It is through Mathematica, which is more of a desktop calculator than a proper coding language. However, they are written very gently, and they will introduce you assuming nothing beforehand. So the level won't be... This isn't a computational subject, although computing skills are extremely valuable for every mathematics graduate, and you should all endeavor to get some before you leave. But this is not about that. It is just introducing you to a tool that will be helpful to you throughout your mathematical studies. There will come a point where the equations are too hard to do by hand. That is what these are for, and this will become more and more normalized as you go through. This is a chance for students going through mathematics to gently learn to introduce computing alongside their mathematics and see how it doesn't replace the theory, it doesn't replace the geometric intuition, but it can help supplement it. So we assume nothing, it should be pretty friendly. All right, let's learn some vector calculus. This week I might not use the full 3 hours, but we'll see how it goes. What I will assume you know. I am going to assume that you guys are completely down with everything you learned in single variable calculus and linear algebra. If I reduce a question to evaluating a single integral, or calculating an eigenvalue, or solving a linear system, I will skip straight to the answer under the assumption that you already know how to do that. If you're a little bit rusty, it might not hurt to revise. I am going to briefly retread, however, the stuff that you learned in 1962, the multivariable calculus stuff, because I've met students before, and I know that half of you ran a magnet over your brain over the summer break and remember very little of what you learned. So, however, it will be a little faster and a little more theoretical. So I know that everyone is rusty, and in fact, today should hopefully be revision for everyone, and most of this week. We start on some new stuff next week before really going for it in week 3. So, the thing about vector calculus is that it's all multivariable for the most part. Everything we do will be in some way a multivariable problem, and that means we need to remember the most important concept you learned in multivariable calculus, which is partial differentiation. This isn't a trick. The partial derivatives of a function of several variables is obtained by fixing all variables but one, but the one you care about, so pretending that they are all just constants, and then taking the ordinary derivative with respect to the leftover variable. Remaining variable. Normally I won't leave large blocks of text for me to write in, but I will occasionally, just to let you take the time to take in the important idea. And the notation we use will be partial f, partial x, or fx. We will use these notations interchangeably, and derivatives will go from, if there are multiple, which you will see a lot, derivatives go from left to right. This should hopefully be familiar to most of you. So what that means in the context of a multivariable function is that we have some function of x and y. So let's say we've got x and y, and this thing here is f of x and y. When I refer to the graph of a function in x and y, this is what I mean. So this z we will refer to a lot throughout the lectures as the graph of a function in x and y. That is essentially a 3-variable thing. There's an f, there's a y, and there's a z in this surface. but once you have x and y, you can trace out z. So if I am living at some x naught, y naught, some base point, and I want to take the partial derivative with respect to x, I fix y, pretend y doesn't exist, and then I ask, what is the partial derivative what is the full derivative if I'm only considering in terms of x? And similarly, if I want the partial derivative with respect to y, what I do is I fix x and look at how f is varying in the y direction. This, I think, is fairly self-explanatory to a lot of people and does ask the obvious question, what about all those other directions? And I think you've seen the answer before, but we will go over that again, just so you have no excuse. But before we do, we're going to dust off the rust a little bit and prove something. We're going to prove something. You're never going to have to reproduce this proof, but it's mostly to get back in the system of what doing rigorous advanced mathematics is. We're going to suppose that the partial derivative fxy exists and the partial derivative fyx exists, and they're both continuous. In that case, fxy is going to equal fyx. We just want to establish that so we can use this freely for the rest of the semester, and it's also going to remind us that the mean value theorem is very important. So, we're going to do this proof, bit long, bit involved. Clearly, these exist in a continuous, which means the limiting definition of their derivative exists. So you'll remember the limiting definition of the partial derivative is just the limiting definition of the derivative with the other variable being held constant. So it's the limit as h goes to 0 of f of x plus h y minus f of x y all over h. Something you learned in middle school, let's say. Okay, and we're going to call this equation 1. And we're going to define fy in the same way, limit as h goes to 0, except now x is fixed and y is permitted to vary, all over h. Okay, so these, we'll call this equation 2. Starting with the basics, building up. What we're going to do, so just a note, these are fixed. And in this case, it is the x's that are fixed. So that's the difference, in case you were playing Spot the Difference and missed it. So by substituting 2 into 1, we get the expression that we actually need to say something about, because we are interested in the derivative with respect to x and y. So if I take the expression for xy and then if I take the expression for fy and then do this operation to it, what you should hopefully see is that this is equal to, and we term this fyx because we did the y derivative first, is equal to the limit as h goes to 0 of 1 over h times the limit, we're going to make this one an L goes to 0 of f of x plus h y plus L minus f of x plus h y. So we've fixed this one at x plus h, and we're going to subtract away the limit where instead of fixing it at x plus h, we fix it at x. X, y plus L minus f of x, y all over L. Ugh. We handwrite math. You are used to that by now. I don't need to explain why we do that. So we can pull all the limits outside and write this expression as the limit as h goes to 0, the limit as L goes to 0 of f of x plus h, y plus L, minus f of x plus h, y, minus f of x y plus L plus f of x y all over HL. And we're 90% of the way there because all of this commutes. This is all nice and can be done in any order. The only thing that we're not certain commutes is the limits. You don't know for a fact that limits commute. So we have this limit here and this limit here. To prove our theorem, we can find, similarly, fxy equals the limit as L goes to 0, limit as h goes to 0, of the same thing, because everything inside the brackets commutes. So what I have to show to prove my theorem is that the limits commute. To prove, show limits commute, i.e. limit does not depend on order. "90% of proofs in math are just starting with a definition and then torturing it until it's in the form you want it to be. We will do a lot of that, but this is a good start. Okay, but we don't necessarily have many tools. We're going to define this new quantity, capital F. Capital F is a function of h and L, which we're going to say is exactly the thing inside here. So we are interested in how this varies with h and L. And remember, if we can swap the limits of this function f with respect to h and L, then the proof is complete. So it makes sense to ask how it varies in terms of h and L. Because if it varies nicely in terms of h and L, then everything is free. And to do that, we're going to use maybe one of the most important theorems in mathematics, the mean value theorem. So you've seen the mean value theorem before, and then you've probably not used it much since. We're going to use it here and there, as and when it's necessary. If we have a continuously differentiable function g on some interval of any size, it doesn't have to be small, then there exists some theta such that the derivative with respect to x of g of x plus theta h is equal to the average slope between the two, g of x plus h minus g of x over h. Probably at some point you use this to prove the fundamental theorem of calculus, and then you forgot about it forever. What that means visually is that if you have some curve which has some average slope between 2 points, then there is a point which we call x plus theta h, where the slope is equal to the average. Theta being between 0 and 1 just means that point can exist anywhere in here. This is an existence result. It tells you that something exists without really giving you any information about what it is or where to find it. But we don't care, because we are eventually going to be squeezing that point into a very narrow range, and that is good enough for us. All right, now we have about a slide and a half of algebra games. So what we're going to do is let phi of x be a function, and that function is f of x y plus L minus f of x y all over L. Okay? Should be clear that we have picked this form so that we can apply the mean value theorem, and we will eventually be replacing this with this for some theta that we don't know. So we're going to do precisely that. But before we do that, we're going to express this capital F of HL in terms of this new expression, because you should hopefully, and it's probably not obvious to look at, and you may need to poke through the algebra to see this, phi of x plus h minus phi of x all over h is actually a way of writing this function up the top. And you can see this. If I take this, and everywhere I get an x, I replace it with an x plus h, and here I preserve it as it is, then I will get that expression up the top. It's quite nice. Okay. The mean value theorem tells me that there must exist some theta 1 between 0 and 1 such that the partial derivative, because remember, if we fix this is one variable, but now this is not one variable, but we can fix y and treat it as one variable, so we're not doing anything too tricksy here. Evaluated x plus theta 1h is equal to precisely this thing above. All right, not super revolutionary, but what that means is we've taken an expression that is fully sums and we've turned it into something that has an exact derivative, evaluated at an inexact point, but we're like homing in on the answer. Okay, so therefore, recalling what phi was, f of hl is equal to phi x, x plus theta 1h. So taking the derivative of this with respect to x gives me partials on the top. Equals fx, evaluated at x plus theta 1h y, minus fx. And these are both at x plus theta 1h. So the only difference between these is in the second quantity. But all I've done here is algebra. Let's talk about the intuition. The intuition is simply writing this expression, which is the thing we need to know about, in a form where we can apply the mean value theorem. And then we're just going to apply the mean value theorem a bunch of times. And then we're going to write it in a different way. It might not surprise you to know that we're going to write it in terms of a y variable, use the mean value theorem, and then pull everything down to show that they're equal to each other. So we're going to do the same thing, but from the other side. This is basically the exact same arrangement, except what we're going to do is we're going to start with this fx. So instead of starting with just an f, I'm going to take it as a given that this has been done and define a new function, f of x, x plus theta 1h, y. So if I go back and compare this new expression with what I have up here, I haven't really changed anything because f of hl is equal to this thing, and I'm just going to replace these fx's with my new function psi. Psi of y plus l minus psi of l all over L is equal to exactly what I had before. So all I've done is started with this and written it even more simply so that I can apply the mean value theorem again. So now I'm going to say there exists a theta 2 such that stuff looks like this expression. So there exists a theta 2 such that f of hl is equal to psi y of y plus theta 2l. All we're doing is iterating the mean value in the theorem in both directions. So I've reduced this to a function of y. I mean value theorem it. And what that tells me, and this is very nice, is equal to psi of y, y plus theta 2l, which if I go back to what psi represented, which is fx, then this is in fact fxy of x plus theta 1h, y plus theta 2l. So I have taken my limiting expression and written it in terms of the derivatives that it is aiming to get to with the mean value theorem applied in both coordinates. If you only take one bit away from that sort of proof chunk, It is that we can apply the mean value theorem to both variables if our function is continuous in both directions. That's what we have. Without continuing further, that's what we've just proven, but that's not what we wanted to prove, so we are going to take it a bit further. But that is in itself a result. If we reverse the order and do the exact same thing, and, exercise to the reader if you wish, then what you get is fyx. X plus some theta 3h, y plus some theta 4l. There's no guarantee in the proof that we've sketched out that theta 1 and theta 2 are the same as theta 3 and theta 4. For some, theta 3 and theta 4 in 0, 1. Okay. So we've shown that our capital F, this function we constructed, looks like this, and it also looks like this. But theta 1 and theta 2 are not necessarily the same as theta 3 and theta 4. What's the ingredient that's going to make this work? Tell your neighbor. Take a moment, tell your neighbor what I'm about to do. All right, now put your hand up if you think your neighbor told you something sensible. You have no faith in your colleagues. Did anyone's neighbor suggest that I'm about to take the limit as h and l go to 0? Put your hand up if your neighbor told you that. I saw a high five at the back. See, your neighbors aren't stupid. You can listen to them. Okay. That's exactly what I'm about to do, because while theta 1 and theta 2 are not necessarily the same as theta 3 and theta 4, if I compress their region of existence to a point, then they will become the same thing. Question? Theta 3 and theta 4 be open closed? You are absolutely right. They are open. Thank you. I am a bit hand-wavy and might get technical details wrong from time to time. It is absolutely fair game to tell me if I've done something like that. Okay, so what we're going to do is we're going to take the limit as h and l go to 0, 0 of fxy, x plus theta 1h, y plus theta 2l, and we can see, because everything is continuous, that what that means is this is actually, in practice, the limit as theta 1 and theta 2 goes to 0, because we're squishing theta 1 and theta 2 into a smaller and smaller region. I will, yep.
Sorry, top line, sine y plus l sine l, is that supposed to...
Psi y. Good. I appreciate that. You are welcome to stop me, particularly in technical proofs where getting things right is quite important. Is equal to the limit as theta 1, theta 2 goes to 0, 0, which again is really the limit as h and l goes to 0, of f of yx, x plus, oh, sorry, theta 3 and theta 4. Someone was about to pick that up, I have no doubt. X plus theta 3h, y plus theta 4l, which tells me that my limits are continuous. Which tells me that my limits can be my derivatives can be interchanged. This was a quite involved analysis-y proof. This is not mostly the flavor of the proofs that we're going to do. This is more a flavor of a proof that you've seen before to wake you up on day 1 of semester. You don't have to reproduce this in the exam. Don't try and memorize it. What I really want to emphasize is that all of this still is powered by the same engine in the machine, the mean value theorem. And everything we do, as weird and as complicated as it's going to get, the mean value theorem sits underneath it all. So in general, if we have some function f on an open set in Rn, and all of the mixed partial derivatives with a certain number of differentiations exist and are continuous, then they are all equal. We can always say that fx, x, y, z is equal to f, y, x, z, x is equal to f, y, z, x, x is equal to, you get the drift. In this subject, we're going to take this as a given. Obviously, if things are not continuous, if they blow up, if lots of complicated things happen, then this becomes a little dicier. You probably met that in multivariable calculus. All of those complications exist in vector calculus, but I'd like you to learn vector calculus before you worry about all of those. So we're not going to lose too much sleep over that. Okay, so what are the weapons in our arsenal to attack vector calculus? Well, the next thing, hopefully a thing that you've seen before, is linear approximations and tangent planes. I dreamt about tangent planes last night because I was thinking a lot about this lecture. Don't do that. So, a reminder of tangents in one variable. The local linear approximation of some function f is equal to f of x naught, the value, plus the slope x minus x naught. And what that gives me is something that looks like this. And this is my local linear approximation. You can keep going and take more terms and put together a Taylor series, and that is a very admirable thing to do. But we are going to be focusing on the tangent spaces for all intents and purposes. And the reason we're going to be doing that is not just because the algebra is easier. Why am I only going to be interested in linear tangent spaces? Anyone want to take a guess? No wrong answers. More or less. Yep. The idea is other shapes might not follow the curve very well. Locally, they'll follow it better. Far away, they'll follow it worse. But we're going even deeper than that. If stuff is linear, we have a very powerful tool in our arsenal. You had a whole half subject dedicated to it. What was it? Linear algebra. That's right. Tangent spaces are so powerful because they let us convert calculus problems to linear algebra problems. And we will be couching this in the language of linear algebra. So what about two variables? We have some graph of a function xy. And what we're going to want is something that looks like L of xy, which is the right value at some x naught, y naught. So at some x naught, y naught, the value is correct. So that sort of takes care of itself. Plus some constant times by the variation in x, plus some other constant times by the variation in y. And what remains to find out is what is C1 and what is C2. Fortunately, we can apply an extra condition, and the extra condition we applied here to get f dash was that their derivatives had to be the same at this point. So, by extension, the thing we might want to figure out to get C1 and C2 is that their partial derivatives have to be the same at that point. So that tells me that the partial derivative of L with respect to x should be fx of x naught, y naught, and the partial derivative with respect to y of my local linear approximation should be fy of x naught, y naught. And a little bit of algebra tells us that the only way this happens is if that is C2 and that is C1. So, f of my local linear approximation is f of x naught, y naught, plus fx at x naught, y naught, x minus x naught, plus fy of x naught, y naught at y minus y naught. You might think that everything is basically the same. It starts to get a little more complicated as you keep going down orders because you have cross terms and stuff. So actually the expressions for second and third corrections and the like to higher order Taylor approximations, you probably met them in multivariable calculus, but in case you've forgotten, involve more complicated things like the Hessian. Okay, so we have our local linear approximation, and that defines a plane. A plane which is linear and lets us use linear algebra. And a way of characterizing what's going on here is my local linear approximation is that plane and it is perpendicular to the normal vector at that point. So I have some normal vector. It will often be the unit vector, and I will often put a hat on it. So the local linear approximation is perpendicular to the normal vector at a point, and in fact, that's going to be a slightly more fundamental definition that we will get to. But we'll do a bit of an example because we all like calculating stuff. If we have some local linear approximation, then we can go back to what we learned in linear algebra, and we can say that the normal vector at x0, y0 has to be n is equal to minus fx minus fy 1. And that is a linear algebra result. I won't reprove things that are just straight linear algebra results unless it's particularly important to what we're doing. You should hopefully be able to determine that that is true. Okay, so as an example, I have this surface here. Z is equal to x squared minus y squared. I want to know the tangent plane at 1, 3. Because I am committed to getting you out on time every day, I am going to do these calculations myself, but normally I would give you a bit of a chance to do it. However, you can all take differentiations. So the derivative with respect to y at x0, y0 is going to be minus 2y0. So our normal vector, which I'm just going to put together in exactly that way, is minus 2x0, 2y0, 1. This isn't a unit normal because, of course, there's no way this has absolute value 1. It is, in fact, x0 is equal to 1, so that's minus 2. Y0 is equal to 3, so that is 6. Minus 2, 6, and 1. Hey, look, this surface I sketched is that. So this vector is minus 2, 6, 1. Pretty straightforward to calculate. I don't want you to memorize formulas. I want you to understand where formulas come from. So you should, if you don't remember why that's true, go dig through your linear algebra notes. Which means at 1, 3, I can evaluate stuff, and I can get f of 1, 3 is equal to minus 8. I can get fx of 1, 3 is equal to 2. And I can get fy of 1, 3 is equal to 6. So I can put together my local linear approximation, minus 8 plus 2x minus 1 plus 6 minus 6. That didn't seem right. Minus 6 y minus 3. Or, if you like, the plane 2x minus 6y minus z is equal to minus 8, which hopefully you remember how to construct from first year. Okay, so we've got tangent planes, we've got normal vectors. There's one more ingredient before I'm going to let you go, which is the chain rule. No, you know what? We'll pick this up tomorrow. It's fine. This segues better into the next bit anyway. All right. Before you go, there is one thing I'd like to ask of you. And you were really good about this today. This is something that tends to drift as the semester goes. I will always commit to getting you out on time. You have places to be. Your time is important. But don't start packing up with 5 minutes to go, otherwise everyone starts packing up, and that's very disconcerting to teach to. You were great about it today. I have no reasons to believe you won't continue to be that. I'm just asking you to bear that in mind. All right, I will see you all tomorrow for 3 hours of madness. Hi. I would like to, but it's a bit tricky for people who are on the other side of the room. The thing about this screens is there are places where it is only really possible to see one properly. So I get the request, it makes a lot of sense, but there are reasons why I don't do that.
Is the number in the title of it corresponding to a textbook?
Yes, that corresponds to the chapter from the calculus textbook.
Thank you.
No worries. Hi.
The very last one.
Of course.
I've been looking up in 10 minutes. Thank you.
It's on the big screen, so I'll just field these questions. Thanks. Hi.
With this one, the normal vector,
Yeah.
is this just taking a cross product and scaling it?
Yeah.
Okay.
More or less. Or showing that any vector in that has a zero dot product. That's actually
So
how.
it's the same sort of thing.
Yeah, so imagine breaking that down into two unit vectors. Whatever unit vectors you produce, the dot product with that will be zero because of the coefficient.
Sure, but then how do you identify that it's this normal or not?
You don't, that also
doesn't matter?
works.
Because you can scale this out.
Yeah, we just defined a normal.
Sure.
There's no one normal. Normal is the set of normal vectors has that as a basis vector.
Yeah, right.
Good.
Cool.
All right. See ya. See ya.